So previously we have seen the what are the method of recording electrocardiogram. So the what are the different leads we use in recording? There are the bipolar leads, there are the unipolar leads, there are three bipolar leads, there are six unipolar leads. Uh, nine unipolar leads. So out of that, three augmented and three chest leads. So the the unipolar leads, uh, augmented, and six chest leads, different combinations of these leads, and that we have seen. Now in this, we see what are the different waves in ECG, what are these their reasons for these waves, what is their normal interpretation. If you see this conducting system of the heart, okay, this is conducting system of the heart consists of SA node, AV node, bundle branches, right and left bundle branches, Purkinje fibers. So impulse originates from the SA node. Impulse travels from SA node to the right atria, left atria, and to the AV node via the internodal pathways. The internodal pathways, the anterior, middle, and posterior internodal pathways. From the AV node arises the bundle of his. From bundle of his, right and left bundle branches, and then the Purkinje fiber arises, which supplies the respiratory ventricles. In diagram, you see this impulse arises from the SA node. Impulse passes to the right atria, to the left atria, and to the AV node. And from that AV node arises the bundle of his. There are two branches, right and left bundle branches, and through this bundle of his, organic fiber arises and which supplies the right and left ventricle. That's how the depolarized wave from arises in the right atria. It spreads throughout the heart via its conducting system. Basically, when we talked regarding the leads, I said that where is the placement of the positive electrode? That is the point, or that is the you suppose we place the camera or your eye and looking the heart from that side. Lead one is looking the heart from the left data surface. AVL looking the heart from the left data surface. Lead 2 AVF and lead 3 looking the heart from the inferior surface. So they record the activities from the inferior of the heart. AVR from the cavity of the heart. Lead 1 it is it is as a 0 degrees angle. It orients and it records the left data surface of the heart. Lead 2 60 degrees of it's oriented to the 60 degrees of the angle. Okay, lead 3 it's oriented towards the 120 degrees of angle. AVL minus 30 degrees of angle. AVF plus 90 degrees of angle, and AVR minus 150 degrees of angle. So lead 1 is oriented towards the 0 degrees of angle, lead 2 60 degrees of angle, lead 3 120 degrees of angle. AVL it's oriented towards the minus 130 degrees of angle. AVF plus 90 degrees of angle. AVR minus 150 degrees of angle. So actually, By convention, if the depolarized wave moving towards the electrode, it is recorded as a positive deflection. If depolarized wave moving away from the recording electrode, it is recorded as a negative deflection. And if the depolarized wave moving perpendicularly, then it is recorded as an isolated line or biphasic line. If depolarized wave is moving towards the recording electrode, it is recorded as a positive complex. If depolarized wave moving away from the negative recording electrode, it is recorded as negative complex. And if it depolarized wave is perpendicular, it is recorded as a biphasic complex. So that's one thing, and second is that the regarding repolarizer, if the repolarized wave moving towards the recording electrode, it is recorded as a negative deflection. If repolarized wave moving away from the recording electrode, it is recorded as a positive deflection. And if repolarized wave moving perpendicularly, then it is recorded as a biphasic. So the different waves we can record with the normal ECG, it's PQRST waves. Okay, PQRST waves. So these are the different waves you can record with the ECG. P wave is because of atrial depolarization. Okay. P wave, this is the SA atria. This is the right atria. This is the left atria. Depolarized wave is moving towards the recording electrode. See, this is the lead two. So lead two. Okay, this is a placement. By convention, if the depolarized wave moving towards the electrode, recording electrode is recorded as a positive deflection. That's why the P wave is positive. You see this P wave is positive because its direction is to the recording electron. Then QRS complex. QRS complex is because of the ventricular depolarization. QRS complex is because of the ventricular depolarization. That Q is because of the depolarization of the interventricular septum. Depolarized wave moving from left to right. Q is depolarization of the ventricular septum and it's moving from left to right. So it is the negative. That's why it is negative because moving away from the recording electron. R wave, upward wave after the P wave because of the depolarization of the major ventricular mass. Depolarization of the major ventricular mass. So R wave is upward wave after the P wave. And then S wave, again negative wave, downward after the R wave. It's a downward wave after the R wave because of the depolarization of the pulmonary conus and posterior ventral part of the left ventricle. So that's why it is a negative. So QRS is because of ventricular depolarization, but in ventricular depolarization there are different components. Q wave is because of depolarization of the interventricular septum, and interventricular septum depolarized from left to right, so it is a negative. R is because of depolarization of the major ventricular mass, it is depolarized towards the recording, that is a positive. And S wave again negative because of the depolarization of the pulmonary conus and the depolarization of the major posterior part of the left ventricle. T wave is because of the ventricular repolarization, and it is the positive wave because ventricular is repolarized from the epicardium to endocardium. Ventricle is repolarized from the epicardium to endocardium, and that's why it is the repolarized wave. Ventricular is depolarized from endocardium to epicardium. Ventricular is depolarized from endocardium to epicardium, and ventricular is repolarized from epicardium to endocardium. This is the, you see it. This is the uh, paper on which ECG is recorded. If you see, there is every smallest square is of 1 millimeter in size. Every smallest square of 1 millimeter size, and there are every fifth square is marked with a bold line. So every fifth square is marked with a bold line. Every smallest square is of 1 millimeter in size. This is a wax coated paper. You see this wax coated paper. See now calibration of this, as a paper moves at a speed of 25 millimeters per second. This is the speed of paper 25 millimeters per second. You check on that. There is a speed of is standard speed is 25 meters per second. So we choose the speed. So for to move paper in 1 second, 25 millimeters paper moves by 1 second. So to move 1 millimeter, how much is? So it is a 0.04 second on the x-axis. 0.04, one smallest square is 0.04 on the x-axis. On the y-axis, calibration when current of 1 millivolt is passed, it deflects the stylus by 10 millimeters. When current has been passed through the stylus, it deflects the stylus by 10 millimeters. 10 millimeters. So stylus deflected by 10 millimeters. So one small square vertical is 0.1 millivolt. 0.1 millivolt. So P wave is because of the arterial depolation. That I already said. P wave is because of arterial depolation. Duration is 0.08 to zero point 0.1 seconds. Duration is 0.08 to zero point 0.1 seconds. Amplitude is 0.2 to 0.5 millivolts. QRS complex is because of ventricular depolarization. Duration is 0.08 to zero point 0.1 seconds. Duration is 0.08 to zero point 0.12 seconds. Amplitude is 1.5 to 2. So 3 to 4 times bigger than the P wave. And the T wave. T wave is because of the ventricular depolarization. T wave is because of ventricular depolarization. You see it is of 0.20 seconds. 0.27 seconds. 0.27 seconds. This means it is at least 2 to 3 times bigger than the P wave. And amplitude is 0.2 to 2.5 seconds. Amplitude is quite similar to that of the P wave. Then PR interval, atrial depolarization and conduction of the impulse into the bundle of his. PR interval, this is the interval which denotes time required for atrial depolarization and conduction of impulse into the bundle of his. Point is 0.13 to 0.16 seconds. 0.13 to 0.16 seconds. PT interval is the time required for ventricular depolarization and ventricular depolarization, and duration is 0.4 to 0.43 seconds. Then ST interval is time required for ventricular depolation. The duration is 0.32 seconds. So I again repeat, P wave because of arterial depolarization. Time required is 0.08 to zero point 0.1 seconds. Amplitude is 0.2 to zero point 0.5 seconds. QRS complex because of the ventricular depolarization. Time required is 0.08 to zero point 0.12 seconds. Amplitude is 1.5 to 2 seconds. T wave is because of ventricular depolarization. Duration is 0.27 seconds. Amplitude is 0.2 to zero point 0.5 seconds. PR interval, it is time required for arterial depolarization and conduction of impulse to bundle of phase. Time required is 0.13 to 0.16 seconds. QT interval is time required for ventricular depolarization and ventricular depolarization. Duration is 0.4 to 0.43 seconds. ST interval is the time required for ventricular depolarization and the duration is 0.32 seconds. So you see the different segment intervals and disease. Segments, PR segment. PR segment, time required from arterial depolation to conduction of impulse into the bundle of his. It is measured from the starting of P wave to the starting of the QRS complex. It says starting of P wave to the starting of QRS complex. Normally it is 0.12 to 0.20 seconds. Okay. If the PR segment is increased, that indicates the heart block. If there is decrease in PR segment, it indicates Wolff Parkinson's White syndrome. If there is increase in PR segment interval, then it indicates heart block. If there is decrease in PR segment, it indicates Wolff Parkinson's White syndrome. Then QRS complex. QRS complex indicates ventricular depolarization. QRS complex indicates ventricular depolarization and it increases in ventricular escape rhythm. It increases in ventricular escape rhythm. And it indicates the sorry. Then next is the QT interval. QT interval varies with the heart rate, obviously. QT interval varies with the heart, but normal duration is something 0.28 to 0.42 seconds. And it indicates depolation and repulsion of the ventricles. It increases the risk of ventricular tachyarrhythmias. Okay. Then ST interval. Then ST segment. That is end of SVR to the big to the sorry. Then we have the ST segment in this, which is isolated line between at the end of S wave to the beginning of T wave, and there is elevation indicates ST elevation indicates myocardial infarction, ST depression indicates ischemia. Then, so in short, there are intervals, PR intervals, QT interval, okay, and there is the ST interval. There are two segments, PR segment and ST segment. Okay, PR segment indicates time required between arterial depolation to ventricular depolarization. ST segment indicates the time required from ventricular depolarization to ventricular depolarization. ST segment elevation and depression indicates something. That elevation indicates myocardial infarction, depression indicates ischemia. PR interval should be 0.12 to 0.20 seconds. Okay. If it is more than 0.20 seconds, it indicates the heart blocks. If it is decrease than 0.12 seconds, it indicates Wolff Parkinson's White syndrome. Steps to interpreting an EKG. Rate, rhythm, axis, intervals, PR intervals, QRS complex, QT interval. Then hypertrophy, ST segment, T wave, and Q waves. How to calculate the heart rate? To calculate the heart rate, there is a formula. Heart rate is equal to 300 divided by number of large waves in 1 RR interval. Okay, or heart rate is equal to 1500 divided by number of small squares in 1 RR interval. 1500 divided by number of small squares in one RR interval. That is the heart rate. So one of the simplest way to calculate the heart rate is if you mark the how many large squares it span. If one R wave to the next R wave was spanning the only one large square, then it is 300. If it is spanning two large squares, then it is 150. It is spanning three large squares, that is 100. Four large squares, 75. Then five large squares, 60, and six large squares is 50. That's how you can have one bit. In between two successive R waves, if they span one large square, it is a 300. Two large squares, it is 150. Three large squares is 100. Four large squares is 75. Fifth large square is 60, and sixth large square is 50. That rhythm, how to calculate the rhythm? Check whether there are p waves in the result. If the answer to this question is yes. If there is a p wave before every QRS complex and QRS complex after every p wave, check whether there is every there is a p wave before every QRS complex and every QRS complex after every p wave. Answer to this is yes. Are the p waves and QRS complex regular? Yes, their interval is regular. Are the p waves and QR complex regular? Is the PR interval is constant? Is the PR interval is constant? That's how much is the PR is interval? 0.12 to 0.26. Answer to all these four questions is yes. So this is a normal sinus rhythm. Then how to calculate the electrical axis? To calculate the electrical axis, you require two leads. Normally we choose lead 1 and another lead is lead 3 or ABF. So mark the lead 1 on a graph paper. Lead 1 is marked as a 0 degrees angle. To lead 1 at the 120 angle is marked lead 3. Then find out the RS difference in lead 1 and RS difference in lead 3 or AVF. If RS difference in lead 1 is a positive, mark on the right side. If RS difference in the lead 1 is negative, mark on the left side. If RS difference in lead 3 is a positive, mark below the baseline. If RS difference in lead 3 is a negative, mark above the baseline. Okay. I again repeat. Uh, Lead 1 and lead 3 draw on a graph paper. Lead 1 draw at the 0 degrees angle. Lead 3 is draw at the 120 degrees of angle. Lead 1 at a 0 degrees angle, lead 3 at 120 degrees of angle. On lead 1, mark RS difference. On lead 3, mark the RS difference. Okay, if RS difference is positive on lead 1, mark on the right side. If RS difference is negative, mark on the left side. If RS difference is positive on lead 3, mark below the baseline. If RS is negative, mark above the baseline. Then what to do? Mark the perpendiculars from this point, from lead 1, from lead 3. All the two perpendiculars meet some common point. Okay, the joining of these perpendiculars, joining of this center point, join this. Angle of this is the electrical axis of this ECG. Normal axis is between 0 to 90 degrees. If the axis between 0 to minus 90 degrees, it is left axis deviation. If axis is between plus 90 to plus 180 degrees, it is right axis deviation. If axis is between 0 to plus minus 90 degrees, it is left axis deviation. If the axis is between plus 90 to plus 180 degrees, it is the right axis deviation. And axis is between minus 90 to plus 180 degrees, it is the extreme axis deviation. If axis is between minus 90 to plus 180, it is extreme axis deviation. So when you see the ECG, it is a 12 lead ECG. How to interpret the heart rate, then intervals. Okay, intervals. Your PR interval, it should be between zero point 0.12 to 0.20 seconds. Then QT interval, it is something 0.28 to 0.42 seconds. QRS complex, okay, up to 0.12 seconds. Then rhythm, heart rate, P wave, whether P wave is absent, present, normal, abnormal, QRS complex, wide, narrow, then P to QRS complex, P to QRS ratio, and whether the rhythm is regular or irregular. Then the axis deviation. Okay, and thank you.